Well, I think that you've got to say that probably the Chinese might be credited with having discovered that certain materials will burn. They probably then, that with charcoal, you could get fire. And I think the next stage really was that somebody found that by introducing sulfur into the mixture, you could make something that burned quite violently.
More or less now. It's you next, Steve.
Chemistry in action.
Are you in trouble? Oh, look at that. My God.
Ronald Lancaster, master firework maker. The mixture of chemicals in fireworks varies depending on whether they shoot into the air or burn brightly. Firework chemistry is very complicated.
You have to divide fireworks generally into two very definite groups. They are basically those which are, if you like, variations of gunpowder. They are, for instance, fountains or rockets or things that are propelled or are moving in some kind of way. The other system is totally different, because in that particular case, you have to produce a different kind of substance which will produce oxygen. And you then have to add to it a fuel which will in fact make it burn. And then you have to add to that the appropriate chemicals in the normal chemical system to make it burn the colour you want it to burn. All the good firework makers have men in their employment who know how to adjust the mixtures. It's from long experience.
But long experience isn't enough if you're making fireworks commercially.
Sorry to rush you. One of those has blown up.
A spectacular display like this is possible only because Ron Lancaster understands what's going on in the fireworks. He knows the chemistry. It's much easier to control things if you know how they work, if you have an idea, a theory about what's going on. About 150 years ago, scientists thought that everything was made up of particles called atoms. They thought of atoms as small, solid spheres. Scientists also thought that atoms collected together to form groups, molecules. But what holds atoms together? Real molecules normally don't fly apart at the slightest touch. There must be a reason why atoms stay joined together. It was suggested that atoms were a bit like bricks. The idea was that there's a glue, like mortar, holding everything together. Just as bricks are stuck together to form large structures, so atoms can be stuck together to form molecules. And once they're stuck together, to get apart. But it is possible to get atoms apart if they get a big enough thump. Atoms can be knocked apart, then stuck together in different ways to form different chemicals.
In fireworks, we are really converting various kinds of solids into gases and other solids. And that's a very important definition of a pyrotechnic, because you have a difference between an explosive, which in general is a change from solid to gas entirely, whereas a pyrotechnic is basically a change from solid to gas with some solid residues in addition.
When fireworks happen, one combination of atoms changes into another combination. That's the chemistry of fireworks. Recently, firework make a new piece of chemistry. Changes that start and stop regularly. Now they're experimenting to work out how best to control the effect.
Other people are experimenting with organic materials, and at the moment, one or two people who've moved quite far into this field are keeping very quiet about it because it has some commercial possibilities for them in the firework field, and we all like to get a little bit ahead of other people if we can.
Theories about the way atoms join together, bonding, aren't just found in textbooks. They're essential to firework manufacturers, just as they are to other scientists. For instance, to astronomers like Heather Cooper.
They're not quite the kind of light I'm used to watching in the sky. But at least mine last a bit longer than that.
As an astronomer, what's the question Heather's asked most often?
Most of all, is there life elsewhere in the universe after films like E.T.? And the point is, astronomers actually have made a start in looking for life elsewhere. And the most obvious place to look is not the nearest planet, Venus, planet Mars, which for centuries has been regarded as habitable kind of life on it. First of all, you send space probes there. NASA have sent several probes to Mars, several unmanned probes, and this culminated in 1976 with the landing of the two Viking probes, which actually went and landed on the surface to search for traces of life on Mars itself. It's not that easy, because obviously you're not expecting to see a Martian walk by your camera, not even in anything as complicated as a blade of grass. So they had to be designed in such a way that chemical tests were carried out. The astronomers had to learn a bit of chemistry in order to find out what on Mars.
But that chemistry isn't simple. Around 80 years ago, scientists began to realize that an atom wasn't a solid sphere. It was suggested that an atom is made up of a central nucleus surrounded by electrons. And the electrons are constantly moving. Moving in fixed paths called orbits, a bit like planets going round the sun. It was thought that the electrons control how the atom behaves. The electrons control the chemistry. Atoms behave differently because they have different numbers of electrons. This that atoms are not held together like bricks and mortar. There's no glue. Atoms might collect together because their electron orbits overlap. This is one way the atoms are held together as molecules. Another way is for an electron to be transferred, to jump from one atom to another. Molecules can be identified by the atoms they contain and the way those atoms are joined together. It's that sort of knowledge which made possible the Viking experiments.
4, 3, 2, 1, separation. Descent sequencing, we're at mission event work 0.
The controllers knew what was happening only from radio signals from the actual lander. This was the first successful soft landing on another planet. And this was the first picture of the Martian surface. But as we know, pictures aren't enough. Life is likely to be detected only by its chemistry.
One of the simplest experiments was to scoop up some soil with Viking special scoops and to put it inside a container inside Viking and then to give it a bit of nice warm broth. And as you know, when you give bugs nice warm broth, eventually as it passes through their system, they give off gas. And the gas that a lot of living organisms give off after they've had nice broth is carbon dioxide. And here you have carbon and oxygen, which combine together always in the same proportion. That's one carbon atom and two oxygen atoms, and its signature is quite unambiguous.
The experiment was set up carbon dioxide, a molecule with particular atoms joined in particular ways.
That works superbly at first. The bugs apparently give off an awful lot of carbon dioxide gas, but too much too quickly. If there really were living organisms there, they wouldn't have given off so much. It would have been a much more gradual build-up.
So that experiment didn't give conclusive results, but there were others.
Organic life is made up basically of the atom carbon, which is a very, very complicated atom, which manages, because of the way it's made, to build up into long rings and long chains, which is why organic life is very, very complicated and can make up very, very sort of elongated or complex structures. Now, the point about carbon is that when you heat it, or when you heat up any organic substance, it gives up a characteristic odour, rather like the roast beef cooking for your Sunday lunch. So one of the Viking experiments was to heat a sample of the Martian soil and basically just sniff it for complicated organic compounds coming off.
This time there were no complications, but the results were still disappointing.
The sad fact was there was absolutely no sign of organic odours at all. So it seems that Mars definitely does not have any kind of life. And the point is, why were we bamboozled? Why did we think we found life to begin with and then said, no, it's just chemistry? And in the case of Mars, what we didn't reckon with was the fact that Mars's soil has a mighty peculiar chemistry all of its own. Now, that's not to say that our ideas were wrong. It simply means that we needed more information. And science is not a matter of making dogmatic statements. It's a matter of finding out as you go along. Scientists are like everybody else. They make mistakes, and they need to find out more all the time. And this is the case with astronomy and with chemistry, as in all science.
No doubt the search for life on other planets will go on. What a discovery that would be. In the meantime, another search is going on, not on other planets, but inside matter itself. The search for another way to explain why atoms join together. This is Imperial College in London, an important centre of scientific research. For some time, chemists have realised the idea of electrons in orbits doesn't give the whole picture. There are many chemical facts the theory can't explain. So is the theory completely wrong?
No, it's not completely wrong. It was the best of its day. It was the first theory of its day to try and attempt to move away from the classical picture of atoms and molecules and the way they work. Atoms are made of nuclei and electrons, and it was the first theory that attempted to show how the electrons did chemistry.
The theory wasn't wrong, it just contained a number of assumptions.
There were two main assumptions made. The first one, electrons moved in discrete orbits around the nucleus at fixed distances. And the second one was that the electrons could instantaneously jump from one orbit to the next one, taking energy in, and then jump back again, giving the energy out.
So there are two main assumptions. Are they both correct?
Well, the second one is, but the first one isn't. It's part of the baggage, if you like, that scientists took with them from the old classical ideas.
Another big assumption was that an electron going round in an orbit would continue to go round in an orbit. But why should it? There's no reason for that. Scientists now realise that what we know about the movement of things like snooker balls isn't true for electrons in an atom. In the world of the atom, the rules we're used to don't apply.
Imagine an electron going round in an orbit. Can we actually see it? Well, no, of course we can't, in exactly the same way that when a wheel turns, you can't see the individual spokes. But there's something much deeper than that. How would we even see an electron at rest? Well, we see things normally with light. Now, light has a wavelength. And the wavelength of light is such that it's bigger than the dimensions of an electron. So the light, if you like, would simply sort of smear around the electron, and you wouldn't see it. So we need radiation of the same kind of dimensions as an electron. Sort of radiation would be something like gamma rays. Now, of course, there's an immediate snag. We can't see gamma rays. But there's something even worse than that, and that is that as you make the wavelength of light shorter, it packs a bigger energetic punch. So as soon as the gamma ray would hit the electron, it would knock the electron off course. So you would be left with a situation where you were seeing the electron where it was and not where it is. It's rather like trying to grab hold of a bar of soap. As you put your hand on it, it moves off somewhere else.
Lionel's imagination is working towards the idea that it's impossible to know where an electron is, because when you try to look at it, you move it. Today's scientists now think that there probably aren't any electrons. It's easier to imagine an atom as a cloud of negative charge around the nucleus. The cloud idea is another way of trying to explain how atoms behave, another way of explaining bonding. In this theory, bonding happens when two charge clouds overlap. If the atoms are different sizes, then the amount of overlap is different and the bond between the atoms is different. As this is quite a good way of explaining bonding, should we throw out the old ideas?
Well, it really depends on what you want to do. The theory is a starting point. If you want to, say, explain the way sodium chloride dissolves in water, or if you want to, say, explain the bonding in something simple like methane, it's fine. It's quite adequate at a descriptive level. And taken on that level, it works. If, however, you want to go to more complicated systems, then you'll need a much more complex theory.
Even the cloud theory isn't perfect, but scientists use it when it works best, just as they use the electron theory when it works best. The older theory isn't wrong as long as it's used only in the right place. It still has its place in explaining fireworks and in explaining the chemistry of Mars. It's quite normal for scientists to have more than one theory about the way things behave.
Two continues with